first talk now. So it's Ross Urquhart. So Ross completed his master's in chemistry with drug discovery at Strathclyde, and then went on to study for a PhD also at Strathclyde with Professor Tel Tuttle. His research focuses on the integration of machine learning with quantum methods for studying molecules and reactions. And he's going to talk to us about using machine learning potentials beyond the potential energy surface. So I'll hand over to Ross.
That's good there, Keith.
That's good.
Grand. Okay, thank you very much for the introduction. As Keith said, my name is Ross, and today I'm going to talk to you about machine learning potentials, specifically taking them beyond just potential energy. We'll start off with just a kind of brief introduction about what are machine learning potentials. So they help us combine the speed of traditional empirical potentials with the accuracy of some quantum mechanical methods. That means we typically train them on quantum mechanical reference data, for example, from DFT or from some couple cluster calculations. And the pro of this is that it allows us to predict energies several orders of magnitude faster than quantum mechanical methods can. And the kind of main driving force behind my work is this specific machine learning potential, Anakin-Me, or ANI for short. So this is a second generation neural network potential, which means that it only considers local effects. It struggles with non-local effects for the molecules and things like electrostatics and van der Waals interactions. Anything within a cutoff, kind of 5 to 6 angstrom cutoff of a specific atom is automatically included in. And I'll speak a bit more about how that works in a bit more detail in just a second. ANI itself, though, is capable of kcal per mole accuracy compared to reference DFT data. And this is kind of their graphical abstract from their kind of headline paper. And a calculation that take 52 core hours in a DFT calculation only took 0.3 seconds for ANI to calculate. So how does this actually work? We have this kind of thing here, this kind of overall, see if I can get my laser pointer there. We take our input molecule, and what we do is we split this up per atom type. So we have all the hydrogens over here, carbons, nitrogens, oxygens. And what we do there is we make this AEV, that's an atomic environment vector. And what that does is it encodes the local angular and radial environment of an atom up to a cutoff point. So that's our entire molecular descriptors. The molecule gets chopped up into each atom. Each one gets encoded with an AEV, and then they go through an element-specific neural network. So there's one network per atom. You then get an atomic energy out based on the specific atom gone in. And then what we do is we get all of those at the end and just simply sum them together to get the total energy of the system. And it's mainly so far been applied to small organic systems. Some kind of key references down here. The first paper, the 2017 one, had it only applied to small atoms, including hydrogen, carbon, nitrogen, oxygen. But it's been expanded to cover fluorine, sulfur, and chlorine as well. That's through to, I think, the Devereux paper here. And it's got decent scalability as well. They showed this. They typically only train things up to 8 heavy atoms, but they managed to get good accuracy on systems up to 54 atoms, heavy atoms big. So why do we like them? They're kind of really easy to implement. So this is just some sample Python script. We can import Torch ANI, which is their Python implementation of the PyTorch potential. We just kind of load the ANI2X model. So this is the one that includes the fluorine, sulfur, and chlorine. We import the atomic simulation environment. This lets us just read in a sample XYZ file. We attach the calculator on, and then we can print the potential energy of a molecule. So it's that simple. But what really attracts it to us is how easy it is for us to train. So if we choose a sample theory level, DFT, for example, we then collect all the data from our calculations into a data set. We like to use HDF5 or SQLite just for keeping things a bit more lightweight and easier to keep track of. We can then train the potential on energies or energies and forces. It depends what type of data you have available to you. And then you just simply train that to a number of epochs or until they're early stopping via learning or loss rate. So that's just a basic introduction to ANI itself. What we've actually done with it, though, is we've started to look at things beyond potential energy. So here we look at the prediction of pK for small molecules, in particular, kind of a imidazolium carbene type molecules. And what we did here is we developed some bespoke data sets specifically for this. I'll talk more through those in just the next slide. We took an ensemble approach to system modeling because we find that quite a lot of pKa calculations are a bit static based on one potential structure, whereas if you're in a lab calculating a pKa, you don't really get to choose what kind of state or conformer your system's in. So we took kind of ensemble approach to that. And we produced some accurate prediction of pKa values comparable to kind of state-of-the-art methods like PropCA, and also a previous pseudo-relevant ANI-pKa paper. We also then start to explore kind of the machine learning, kind of looking at the explainable AI side of things, because obviously it can be kind of like a black box at some points. So looking into a bit more of that kind of helped us rationalize some of the predictions we had. So again, yeah, echo my last point. Looking at the data sets we generated about 1.5 million total data points from DFT calculations. We only looked at these 5 atoms, as if we start to include more, then we need to generate more data. And we chose the Omega B97X functional with D4 dispersion correction and the DEF2 SVP basis set, mainly just for the speed of it, just to generate all these this amount of data took quite a long time. So we did 4 data sets here. We did 2 in the gas phase and 2 in CPCM water. And the only differ is the charge. So there's a neutral and a charged data set for both the gas and neutral phase. These are publicly available, I should say, up at the QR code. So I'm just going to talk through the kind of workflow of the paper now. This is kind of the overall thing. We wanted it to be quite accessible. So the draw target molecule stage, we simply did in Avogadro. So it's just a run-of-your-mill molecule that you put in there. You very quickly optimize it within Avogadro using something like the universal force field. So it's quite a rough kind of structure there. We then generated conformers of it. We did this using Crest. This generated us quite a few. We then start to filter those. So we did a quick optimization with Fire to get kind of more relevant structures compared to ANI. So ANI was the kind of loaded calculator behind the Fire optimization. And then the filtration down, we did based on a kind of Boltzmann distribution. So anything within the kind of rough filter at the top here was anything out with 5K capmol of the minimum energy conformer was discarded. And then it was a kind of more rigorous one for the second filter. And because we wanted to keep this kind of integrated, we tried to integrate as much as we could into Python. So obviously we could script stuff like the Crest conformers and stuff into kind of bash scripting and things, but we tried to keep as much into Python as we could. I'm just going to talk through the types of results we got here. So there's 4 things we need to look at here. The global minima approaches are kind of the static approaches. We take one molecule, optimize it fully. That is the molecule we look at. The ensemble approach is the kind of Boltzmann distribution. So that's the weighted pKa. There is the weighted pKa values from the either the DFT optimized geometry or the ML optimized geometry. And these are the 2 that we kind of are going to compare mainly here, the DFT ensemble and the ML ensemble. So we see that here. We're looking at the green values. And that's versus the predicted pKa versus the reference pKa there. And you can see that kind of some of them are outliers here, but really we want to look at the range that we're predicting over here. We're predicting over quite a wide range, a logarithmic scale for pKa between 22 and 34, which is quite large. So over that, we still have a reasonable RMSE of about 1.99. However, if we normalize that over the range, we get to about 0.166. Which is comparable when you normalize to PropCA and ANI-pKa before. ANI-pKa was done over ionizable protein amino acid residues. So they had quite a small prediction range of plus or minus maybe 2 pKa units per residue. So overall, that's the kind of good results we got there. We started to show some kind of explainable. We looked into a bit more of why we had some outliers here. I don't have the time to go into that here today, but again, I'll plug the paper shamelessly. If you can go back and look at the recording of this, you can get the QR code and things for that. We do go into that. I'm just going to talk to you quickly about some work that I'm currently going through just now, which is the enhanced sampling of small organic kind of reactions. I'll go through this pretty quick, Keith, just in case I'm running over time. So yeah, as I said before, we look at quite a static calculation of reactants, transition states, intermediates, products for things and reactions these days, especially with things like DFT. However, at higher temperature, it's a bit more unrealistic. So in this work, we start to explore the use of machine learning potentials to enable kind of enhanced sampling of these potential energy surfaces at DFT level accuracy, but in a much quicker way. So the one reaction here we're going to look at is the amide formation via thiol-ester. So we take these two thiols, we lose H2S to form this middle thiol-ester, and then this is just a rearrangement into an amide. However, we're just going to kind of go over this first step here, which is the formation of thiol-ester in a bit more detail. So what we see here is in red, we have any predicted energies for the stationary points, transition states, intermediate, and so on. And you can see that at minima, so at the reactant, intermediate, product stage, we get quite good description of the energy from ANI compared to DFT. However, when we start going into higher energy things, these break down here. So this difference here is about 10 or 11 kcal, about 4 kcal here, and then here it's just about 1.3. So it starts to break down. So if we look at some enhanced sampling here, particularly through umbrella sampling, we can split this up into different windows and hold a potential over those different windows and hold kind of reaction coordinate within that set window. So what we looked at here in the formation of thiol-ester is the formation of this carbon sulfur bond, and then the formation of this hydrogen sulfur bond. These other two dashed lines are breaking, and our reaction coordinate is simply this distance for this bond forming, add this distance for this bond forming. That's what we see here along the bottom, and we kind of see that here when we look at the kind of energy surface from the WAM analysis, is that originally we just kind of get this kind of jagged peaks, the two molecules interacting, they're not really doing anything. Then we get a sudden spike of going over the barrier. And I'm just going to show you that here. Hopefully this will play. Yep. So we've got them interacting, and then we form a kind of transition state here where we've got the bond breaking. I think I've actually put the wrong video in, but never mind. It still shows the point. We have the bond breaking here from the carbon to the sulfur, and the bond forming here from the nitrogen to the carbon, forming the amide and losing the thiol-ester. And then next we will see the proton here jumping over to the sulfur, which happens here. There we go. It's popped over. We have the amide formed, and we've done all that with our ANI. That shows that we can kind of look at different transition states and kind of maybe get some different alternate methods of finding these transition states, which typically were quite a challenge in DFT. So just some closing remarks, and the MLPs are increasingly available. They get used quite a lot. There's different versions of them, and it's just one. And with the kind of applications we show here, we can show that it's more than just predicting energies. We can start to look at chemical properties and start sampling reactions that previously on scales and accuracy levels is quite challenging or expensive to do. And this is quite important in the modern age. There's a lot of data out there, so we can start to train these ourselves. Then it's even better if we can dial in on these applications and start looking at things in more depth. And generating this data, it's quite expensive, but it's rewarding in that we can start pushing these potentials in the ways we want to go. And with the increasing amounts of computational resources available, it's getting increasingly more within reach for everyone to do it themselves. So I'd just like to extend special thanks to my supervisor, Tal Tuttle, my co-worker and postdoc, Alexander van Teylingen, the Tuttle Lab and Scottish group here at Strathclyde. Find the websites there, and then also our computing resources, Archie West. So yeah, thank you very much, and I'll take any questions.